talk about resistance temperature detectors. And now this is going to differ from thermocouples in the fact where you're no longer using the Seebeck effect. You're going to be using Ohm's law primarily. And what you do is you monitor the voltage drop across the resistor. And because a metal will change in resistance proportional to temperature, they've derived an equation here, which we call alpha. And just as an example, you take the resistance of your RTD at 100 degrees C minus the resistance of your RTD at 0 degrees C. And then to normalize it, you divide it by 100 degrees C times that resistance again. So for a 100 ohm RTD, your resistance at 0 would be 100 ohms, while your resistance at 100 degrees C would be 138.5 ohms. So you would plug those in to the top, and then below, to normalize it, you have 100 degrees C times the resistance at 0, which once again is 100 in the example of a RTD 100, which I'll show you there's different flavors. And then once you calculate that all up, you get alpha, and then that's going to be your linear approximation of the resistance versus temperature over, the 0 to 100 degrees C range. And typical metals that are used in these are platinum, nickel, and copper. And we'll start here with platinum. This is the most common RTD material. And as I mentioned, the elements are available in 20, 100, 500, and 1,000 ohms. And this number is its resistance at 0 degrees C. There's 3 common temperature coefficients depending on what international standard that you're using. 385 is the most common. The important thing to take away from this is that if you're going between different countries or different standards, you want to make sure that the temperature coefficient of your instrument matches the temperature coefficient of your RTD material. But in America, you're going to be using most likely the 0.00392. So here's a chart kind of overlaying a general overview of RTDs. As you can see, they have a smaller range than thermocouples, but they have a higher time response. And because their cost is medium to high, you're going to usually find them in the scientific and industrial industries, but mostly because of that better accuracy there. Now, speaking of accuracy, you can get platinum RTD elements in 4 levels of accuracy. And as you can see from this chart, the better accuracy you want, the less range you're going to get. And the more range you want, the less accuracy you may get, especially at those farther out ranges. So these are things you're going to want to consider for your application. Here's a graphical representation of that. And once again, as you can see, the more accurate, the purple and orange are going to be your more accurate, and they don't go nearly as high in range. Your C is your least accurate. It goes the highest in range, but because of that, that slope there, you're going to sacrifice accuracy. Now, RTD elements are also available in nickel and copper. Nickel, you're most likely going to find in appliances. It's used where cost is an issue, so think air conditioner, refrigerator, those types of things. These elements are usually 120 ohms, and that's their alpha. Now, copper RTD is most interesting to me. Copper RTD is mostly used in electric motors or transformers. And basically the idea is that you already have a coil of copper doing something. So what you're going to do is you're going to, let's say, measure 10 ohms off of your transformer and tap it there and monitor it for temperature. And while this is a fairly crude temperature monitoring device, you're using parts that you already have to detect temperature, and most likely you're going to be using this as an overheating condition. So you're not necessarily going to want to say, okay, what's the temperature of my motor right now? You're going to say, you know, if the resistance of my RTD equals, you know, 1,000 degrees, my motor's overheating, I need to shut it off. And this is nice because, once again, you don't need anything extra. You can use a coil in the motor, or, you know, tap off of your transformer that you want to monitor. Now, RTDs are larger than thermocouples and thermistors, so the probe response time can be slower. But they are making new thin film RTDs that are much smaller, and they increase the response time of the probes. And these thin film RTDs have also made surface measurement possible with RTDs, and I'll show you why here on this slide. Here's your wire wound RTD element up at the top, and as you can see, you have the wire wound around the ceramic bobbin, and then you have your leads. And then down here on the thin film, because it's flat, you can put it directly against the surface, and then instead of a coil like this guy, you have a thin film, kind of a fractal shape there, that basically is going to do the same thing that wrapping it around a bobbin would do. But this is a form factor that's flat, and so you can monitor and get good contact on a flat surface. So the last kind of RTDs I want to go over is a special type called the SPRT, and that stands for Standard Platinum Resistor Thermometer. And this was used in developing ITS-90, and it's a very accurate thermometer. The one they used was used over the range of negative 259 degrees C to 962. And these are made from pure strain-free platinum elements encased in special non-contaminating sheaths. So what you're going to have here is you have the platinum sheath, you have a notched silica cross, basically a ceramic in there that's notched, and then you take the platinum coil and it's threaded finely through those notches so that you have a very exact and very uniform spiral around that. You're going to have a glass head for installation, and then there are your leads for your 4-wire measurement to whatever device you're going to be hooking this into. The construction varies depending on the temperature range. You'll find them encased in glass, quartz, platinum, or ceramic, and it's really the environment that's going to dictate which one is the best for this for your application. And the accuracy on these commercial SPRTs can be as low as 0.25 millikelvin, which is 250 microkelvin. That's incredibly tight. And so we can say there's almost no drift associated with these. They do have a poor resistance to shock and vibration. So if you're going to be carting them around, you're going to want something like this, and you're only going to want to take it out when you're using it. This isn't something you're going to be walking around the factory floor with. So as a primary standard, you're going to use a laboratory grade high accuracy resistance bridge device, or once again a long scale DMM, to measure the resistance of the SPRT. And then, as we've mentioned before with some of these other ones, they do have working standards that have an associated electronic readout that will convert the resistance to a table and then just give you a temperature, so you don't have to work out the calculations yourself by hand. And then to calibrate these, it's going to be the same methods as we saw for thermocouples, but your instrumentation is going to measure resistance instead of millivoltage.